going to take a look at optimizing the area and perimeter of rectangles. So we have a rectangle here, and we'll literally count the units we have. We have 1, 2, 3, 4. So this has a height of 4, and this is 1, 2, 3, 4, 5. Okay, so width of 5. So first pieces we got to remember is how to calculate those two things. So area for a little rectangle, I'll use A for that. You can use different letters because area, depending on the shape you have, is technically different. But area for a rectangle is the length times the width. So L times W, we'll call it, okay? The perimeter of a rectangle and perimeter of any shape is adding all the sides together. So you can call it like side 1 plus side 2 plus side 3, and a rectangle will always have 4 sides. So 4 sides together. Now what's interesting about a rectangle is that your length on both ends here, so those are the same distance, and these are the same distance. So we can actually simplify this a little. We can say it's the length plus the length plus the width plus the width. And because those are the same, if we remember how to simplify stuff, we can say 2L plus 2W. And then there's this little thing we can do with common factoring, and it goes like this. 2 times whatever the length plus the width is, okay? All of this other stuff doesn't need to be memorized. This part's helpful. It's a quick way of calculating perimeter, okay? And this is our area law. So now that we have that information, what we can do is calculate. And then we're going to see if we can figure out how to optimize, like what would be the best shape or type of rectangle for this. So quick reference here, the area of this specific rectangle, our length, we'll say was 5, and our width is 4. So we go 5 times 4, and that's going to give us 20. I don't have meters or anything. We're just going to say units, okay? Units squared, okay? And the perimeter of this one, we're just going to use that formula, which is 2, and then length was 5, and the width was 4. So we're using this formula here, where we took the length, okay? That was our L, so we'll call this was our L here, and we took our width here, this is our W, okay? So in this case, we got 2 times 9, which will give us 18. Okay, so we had a perimeter, we'll call it perimeter of 18. So first thing we're going to do is try to optimize area. So perimeters of 18. I can make another shape. Let's see if we can figure out a general rule for our perimeters here. It turns out, let's say I get, you know what, 18 is not a wonderful number. I'm going to change it just a little, and we're going to optimize for something a bit bigger. We're going to say perimeters at, let's say, let's two numbers that one another nicely. Perimeters of, I can do 2. I want to be able to make a really easy shape. You know what? Never mind. We're going to leave it as this, and it'll maybe drive home our point. If our perimeter is going to be 18, I can build another shape of a rectangle. So we have another rectangle here. Now this one's not going to be to scale. What that means is we're not going to count the units here because they're not actually going to add up to 18. 5. Okay, good. Now for a second I thought I was putting my foot in my mouth. Okay, what we're going to say is we're going to make this one edge really long. So in other words, let's say we have something like 7. Okay, so these two are 7, which then means 14 of the units have been used. So we're going to make up the other 2 here. We got to figure out what else would be left. Well, if 14 of these units are used, that gives us 4 more units, and then we have to divide it in 2. So in other words, we can go 2 and 2. And if we do a quick calculation, 2 plus 7 is 9, and then 2 plus 7 is 9 again. 9 plus 9 is 18. So there you go, check. Perimeter is 18. What about the area? Well, the area would be the length times the width, which is length times width. In our case, our length is 7, and our width is 2. So we have 7 times 2, 14 meters squared. Okay, what we want to do is compare to our last shape. We had a perimeter of 18. Both these two shapes, let's get them both in view. Here we go. This shape here and this shape here. Think of the perimeter being like fencing. The fencing is 18. All we did is change the arrangement of it. When I made it a longer looking rectangle, I ended up with an area of 14. When I tried to make the side lengths closer in length to each other, I got a bigger area, 20. So we're trying to figure out the optimal shape here. Now, it turns out, and this one's a little harder to calculate, but it turns out if we get perimeter, which makes this exactly a square, so it looks, in other words, something like this. If we can calculate it so that it's a square, that will give us the maximum amount of area with, say, perimeter, which is like, fencing in an area. So here comes the question, though. That means all of these side lengths have to be the same, which means our perimeter in this case would be side plus side plus side plus side, but all those side lengths are the same. So in other words, it's 4 times some side. And we know the constraint was 18 as our perimeter. So we got to isolate for 4. So if we do a little algebra, we divide both sides by 4. We get a side length of 18 over 4, which is actually equivalent to 9 over 2, which is about 4.5 units. Okay, so let's see if this is true. 4.5, 4.5, 4.5, and 4.5. Well, 4.5 and 4.5, I can use a quick calculator, and I know that's going to be 9. And we know that if we have a rectangle and we have the length and the width added together, we can just multiply that by 2 to figure out the rest. Well, 9 times 2 will give us our 18. So perimeter is 18. Check. We've got that piece off. Is this going to be the biggest area is the question. And we'll have to probably use a little bit of a calculator here. But to calculate this area, we got to do our length times our width. And in this case, they're the exact same. So 4.5. You got a calculator?
18.5.
Is that what it is? No, it's got to be bigger, no? 4.5 and 4.5. I think it's got to be bigger. We can rewrite this as 4.5 squared. Let's see if we can get a quick calculation of this. We got a little calculator. You want to pass me that calculator there, Cole? So we'll plug it in. Let's see if we can turn this on. There you go. 4.5 times 4.5. Ah, there we go. We get 20.25 units. Now, if I do draw attention, 20.25, if we go way back up here, this shape we originally started with was pretty close to a square, and it was 20 units. So when we made it exactly a square, we got a little more area. We got 20.5 in that case. But that's to show that the idea that the closer you get to a square, right? So let's almost zoom out so we get a better idea here. The closer we get to a square. So this one here, very not square-like, only 14 meters. This one, pretty close to square, not exact. We went up to 20 meters for area. And then this one is an exact square, be 20.5. Now, notice that we did is we kept shortening the length. The length went from 7 down to 5 to 4.5. If I make this short side shorter, I can turn this into a 4, which would make this into a 5. Then all I have is this rectangle again. It's the exact same rectangle, just flipped on its side, and we already know its area is not as big. So this is our idea of proving that to optimize a rectangle in terms of the maximum amount of area, we want to make a square when we go through this process.